Hi everybody. So yeah, I give the perspective to most people here. I don't benchmark anymore. I just try to run my production system, which has a different feel to it. But first the question is, why provide a public Sparkle endpoint? It's just a hassle, isn't it? I mean, the things crash, they never really run the way you want them to. But there's a very good reason. We're a public data source. We get funded by the scientific community and taxpayers to provide the data. If you can't get the data because we put it in our own private data warehouse, what was the point? And it's very important that this data is available because a small biological lab doesn't have the budget to make a big data warehouse for all these different data sets. And yet you can't really afford not to have access either, because for the very difficult life science questions we have today, you need to do cross-database queries, because you might be interested in a gene in rat, but you will want to know what the same gene or the similar genes in mouse are related to, and in human. And is your mouse strain actually representative? And lots of very hard questions. You want to know what other people know about those genes. You want to know what they interact. So it's very, very, very broad, very deep graphs, quite common to see queries with 200, 300 joins, as much as single join ones. And well, classical SQL is very nice, and it is actually provided on the web. Warmbase has a MySQL instance, UCSS has a PG Postgres instance, and you can actually access them over the internet. It's not practical, unfortunately. There's no federation, there's no standards adherence. I thought I knew all the ways to ask for the list of tables in the database, and then Virtuoso last night gave me a new one. So is it list tables, show tables, my tables, select star from user tables? Practically, SQL standard adherence is very low. Document-centric REST is definitely not enough for our use cases. SysProt, which is the highly curated, manually looked at subset of UniProt, much smaller than all of it, has been available electronically and what would you call today as a REST interface over email since 1986. For people who, at that time like me, were running around in diapers, this was before you had to add in your email address, but it had get entry name. It was a full representative state transfer, or basically an RPC call. So that's why you provide it. And it looks like this. It's newly updated to the new house style website. You have some query examples, a little bit about the news. And you can see that now we have 19 billion and 300 million and some triples in that data set, which is a significant number. If you look at it in uncompressed and quads, that's about 4 or 5 terabytes. XZ compressed RDF-XML, it's actually a lot less. It's about 136 gigabytes. XML kind of formats is similar. It's monthly updated, so we have a very strict production cycle. And people get very annoyed when we don't meet our production cycle. And you might say our production cycle is 6 months. No, we have 6 days. And 6 days, which includes 1 weekend. So if something goes wrong, I have to work over the weekend. I don't like working over the weekend. So it's basically you have 4 days. Production-wise, it's actually quite a simple website. We have a simple load balancer in front and 2 nodes. Nothing extreme, 64 CPU cores, a 1/4 terabyte RAM per node, 2.5 terabytes consumer SSD. If it dies, we copy it back from tape and we just build a new node. So resilience is replication from tape, and then just hope that not all the hardware burns at the same moment, which, as it's one data center in experience, does happen. Not recently, thank God. We have a custom UI, which is basically a Tomcat with Sesame as our HTTP server. And then Virtuoso behind. We do some interesting things with Virtuoso. For example, every time we start Virtuoso up, we build a new user account with a new password, with a new random user, limited privileges, and then delete everything that was done before. We really try to minimize the amount of attack surface that a public Sparkle endpoint has. So we have 2 Sparkle query parsers. We first parse it with Sesame, then with Virtuoso, to really try to avoid any kind of injection attacks and privilege escalation that comes from running a database which allows anything to happen at all. It hasn't happened yet, but we really don't want it to happen. So we have defense in depth. We have a dedicated machine for loading and testing. It's a classical data warehouse in that respect. You have the 4 days we load it on one machine. We then tar it all up. We put it a copy in our tape library, and then we take that entire database, deploy it, just copy it onto the real nodes, switch the instances, and restart. So switching databases between is basically a zero downtime operation. The load balancer will take care of it. Loading RDF data these days is a completely solved problem. 500,000 triples per second is everybody manages that, I think, which is on the commercial side quite possible. You can quickly hit the ZZip, gunzip limits on our machines. XZ is a bit slower. Higher values of that are definitely possible. You just need more hardware, more parallel readers. Our quarter rack Exadata, when we tried, did 2.5 million per second, and we can push that higher, but then we just need to connect the InfiniBand of the Exadata with the InfiniBand connections of the data, our cluster, compute cluster. And currently that's 100 megabytes per second T-base, which is unfortunate, but otherwise that can go higher, and everybody basically, in production-wise, data loading is no longer a problem for RDF databases. However, we do have challenges. The query load as a public provider is extremely variable. We definitely have a major change depending on who's doing the querying, how the querying are done. Query planners of external parties make a big difference. Is the query a federated query one entity at a time, or is it vectored, where it asks 1,000 entities at a time? Really makes a big difference. The simple data discovery queries are really hard. I'll go down to that in a second, which isn't really the normal users, which will ask very specific questions normally, but this is more, how many things are there? Query timeouts are not really sufficient. In practice, they work okay, but it basically means that our hardware is underutilized. Either we are too strict with them or too flexible. And we are also limited by what can HTTP reasonably support. If you don't answer with your first byte within 5 minutes, your HTTP connection will die. But yet we want to be able to answer really, really hard questions which take 4 days to run. That's acceptable behavior, because the current solution is make some PhD student run for 4 months. So what do you rather run, 4 days on the database or 4 months on your PhD study? These are not quite months, but these are queries per Uniprot release. They're on the log scale. That already says that the amount of queries per month varies a lot. So the peak was 35 million in a month. That ends up, that peak, that was about 50 queries per second. This is over public HTTP traffic. It's a mix. Most of them are select, so that is the large majority. Ask and construct come as well. And describe was mostly robot driven. And we've become a little bit better with our robots TXT, so that's now less. But that's not a very large number either. Real users is always very hard to really get a good estimate, especially because many of these queries come via federated services. So we have mostly of our partners at EBI who have also virtuoso instances. So you'll see a lot of federated queries. So it's always a good guess of like how many real people are that. And the low estimate is basically 300, which is basically the unique user agents, to 2,000, which is what that normally corresponds to with Google Analytics and things like that. You could say that's about the number, which is not a whole lot if you think about it, but for an academic site, for very, very specific questions, it's it's worth the investment that we put into it. The main uniprot.org website would have 30,000 people on a normal day, so it is not an insignificant number either. Now I'll give you one of the really hard queries, and it is basically how many URIs are there in this database. And it basically looks at, give me the URI on the subject, predicate, and object position, and then does a filter for them being distinct and then count them. So it's a very simple query that people like to ask to say, what's really in your database? And well, you can imagine that's actually quite a difficult query because there's each one of them is about 3 billion possible values. So you build a hash set and then you merge those 3 billion hashes in 3 times and then you filter them and then you do the count at the end. And that takes about 10 hours, 9, and well, maybe it crashes our database if there's too many other databases or users running around. But if you actually knew how Virtuoso stores the data, you do select count ri_id from RDF IRI. That takes 18 minutes and gives you the same answer. And I was looking into maybe there's something with static sticks. You can do something even faster where you don't even do this kind of querying, just look at your index size on this value. But compilation-wise, as a query planner, that's not going to be found because the original query is basically of the form that isn't really going to be translatable to direct answers like that. And there's more systems which have similar problems. For example, GVM, the Java Virtual Machine, where you could say, how many bits are set in a long? Well, they have a method for that, it's long bit count, and you can get an answer in Java. And then you get some code like this. It's not the only code for it. There's more GVMs out there with different forms of code. Do a lot of bit shifting and adding and subtracting and anting, or you can do 186 instruction, which is a pop count. And the GVM JIT is never going to go from this very long method to that. It's just because it's a unique instruction and a unique path, it's never going to happen. So the GVM is something what you call intrinsics, where you basically say this method is the same as that x86 assembly instruction. So just don't even invoke the compiler for that, just immediately put that intrinsic there. And that can also be applied for some of these very hard analytical queries because most of the time the database actually maintains this information for its own query optimizer. So you basically have to figure out if a query template matches some information construct that the database maintains anyway. So difficulty of there, of course, is query normalizations. There are many ways of writing that same query. All the variable names can be different. It can be a construct instead of select. It can be a sub-select. All these things are difficult, but it's something to look into. Similar query, this is just try to count all the predicates. Again, which predicates are there? How many predicates are there in this data set? Basically, it's schema discovery. So what you would do in show tables, show columns in a SQL, this is basically the Sparkle standard way of doing it by hand. For GraphDB, this very same number is actually stored because GraphDB maintains predicate statistics. Because that's key for join reordering for them. That entire query could be answered from there, but it isn't. It actually ends up being multiple scans over the entire database, which, if your database is 600 gigabytes long, takes quite a while, with 500 megabytes per second. So even in the most optimal case, you're bound by your, linear read of your SSDs, which is not fantastic. In deploying a large database like this, all the databases have challenges. I actually have managed to crash every single database technology I've ever touched. That's many of them. Challenges for Virtuoso are transitive queries, which is for us a big problem. We have very large hierarchies. For example, taxonomy is a tree with more than 1 million nodes. People start from node number 2, bacteria, and they get back 600,000 nodes in the end. That goes through a tree depth of about 50. That becomes a very large transitive join. Standards compliance is not 100% perfect yet. It's much improved. GraphDB has the other problem, where analytical queries, which does entire database scans, is a big problem. And that really kills GraphDB, unfortunately. I also have lots of experience with Oracle 12, where it's more of a, can we get enough DBAs to actually figure out how to deploy the bloody thing? And then when you deploy it, it isn't really quite like any other Oracle database. It has a global RDF data space. And it's really hard for that reason to manage as a normal Oracle DBA, which is a pity because standards compliance of Oracle 12c is actually amazingly good. I've ever only found one deviation from the standard, and that was a fixed and a half a day. The public monitors which ask these difficult questions are actually very important for us because they help us make sure that our quality is good. Is the data space up to date? Is it accessible for other people? But they also have problems. It is actually a good service, but the uptime is lower than databases that are hard to keep up. They willfully ignore robots.txt. They don't have enough community support. And unfortunately, what you have in Sparkle is service descriptions. You can put a lot of information about what is actually in the database in the service description. So what predicates are there, how many data is there. And in any case, we put most of this data in there. So all these queries are already been answered. They're HTTP get away, but nobody's reading them. And they don't really obey HTTP caching protocols. So we do always say last modified because we only modify the database once a month. So if you ask that query and you got an answer, you don't need to ask the same query again that month. That's why you have HTTP headers. We also have our main website, which is quite a different beast. It's key value orientated with full text search. But we would like not to have to maintain that key value database. It's a very nice database, Berkeley DB GE, with lots of custom bindings. It's a few thousand lines of code that is maintained. We need to fix it every year. And we have enough formats to parse as we have anyway. We have too many formats to support anyway, so one less data format would be great. So if anybody's having a key value oriented Sparkle endpoint, it would be really nice. So that's actually ask for a graph, where the graph corresponds to what you would see a Wikipedia entry, a Medline entry, or in our case an input entry, and you get just a bag of triples bag. And for us that goes between 550 and 5,000, maybe 50,000 triples, and get the whole named graph in a single I/O operation. It's actually the same order of magnitude as what you do for current graph databases, because it would basically be one lookup in the quad table, and then for every triple you would look it up in the different value tables. So it's much better than the relational database, but it can be better. So if somebody wants to orientate their graph database to be mostly key value for the performance and then analytical on demand, it would be nice. There would be a market for it. Small market, but there would be a market for it. We're not the only database which does Sparkle in the Swiss Institute of Bioinformatics. We actually have a number now. It's growing because it's actually very easy to deploy, and it's very nice to keep our data model as it is in reality. So when you make a chemical data structure and the RDF data structure, they tend to match very nicely. We don't have to do a lot of molding to get it in the database. And for most of our databases, performance is more than good enough. We're getting into the point where we're kind of like, well, it takes 2.5 seconds, can we get it under one? Kind of behavior. Well, before it was, well, it takes 4 days of hard handwork to do it. So it's performance-wise, it's good enough. Maintainability is good enough for most people. And your product is large. It's getting smaller, but it's large, larger than what most people have to deal with in its interconnectivity. If there are any questions, I'd be happy to try to answer them.
Any questions?
What do you mean with Uniprot is getting smaller?
Thankfully, biologically-wise, we have now about 95 million primary database records, let's say, call them. And about 40% of them are from bacteria, and they look a lot like another 10% from bacteria. And we're doing some merging for those which are rather redundant on the biological sense. So we get less primary data records, which means that the entire database shrinks to about 40%. which means that we'll be, well, a lot smaller. We don't really know yet how many less triples that will be. That might be not so big a difference, but I do expect the database to be a bit smaller because we just do more compression on biological sense, which is lossy compression, but for the biologists it makes a lot of sense than what we were currently doing, which is basically every time we sequence something, we make a new record, even if that record actually says, well, we already sequenced it. So it's more data deduplication on the, on a conceptual sense on the bio side.
And how big is the data that, I mean, it's getting smaller, but how big is it actually?
Well, XZ compressed, it's now 130 gigabytes in RDF-XML. If you uncompress that into N quads, last time I tried, it ends up being somewhere around 4 to 5 terabytes flat file N quads.
How large is it in virtual operation?
It was, the latest database dump was 1.1 terabytes, but that has increased for some reason and I haven't quite figured out. Before it was about 600 gigabytes. So I still have to figure out what we did. We did change some of our data model, so that might have changed the behavior for it. So it's not a big data, but on the other hand, we've done a lot of effort to make it all very small again. So we have a lot of techniques to make sure that every time we reference something, it's actually the same thing. So we do a lot of cryptographic hashing to make sure that the same values get the same IDs, even if you don't have shared primary keys, really reducing the space. If you look at it for our Lucene text, full text indexes and Berkeley DB compressed stores, they're actually in the same order of magnitude, size-wise. So it's also about 600 gigabytes.
But it's not extremely large. Sorry. Have you ever considered putting your data on Amazon? Like they actually would host it for you for free and charge people for basically using it?
Hosting it at Amazon, last time we did the calculation, would cost us about 120,000 US dollars a year.
But it would not cost you anything probably. They would charge your users for that.
Well,
I mean, the whole Web Commons is there, it's for free. I mean, to store it. And then people are charged for using it.
Yeah, but you have to do the upload charge. And then all the users pay for it, and the users already didn't have money. And then you have to figure out how to use Amazon, and then you have to use credit cards in the academic instances. And then all becomes practically unusable for our poor lab biologist again.
Okay, we'll take it offline.
A quick one.
Plenty of questions, but first one is, have you considered using Neo4j or Titan or any of the more this branch of graph databases for the same job? That's
okay.
Question one. Question two, I'm aware that you have nice experiences with doing this data integration that you have to do using Spin. I assume it would be quite interesting experience to share with this audience.
I'll try to be very, very quick in it. There's a public project called Bio4j, which uses Neo4j. My professional experience is that it solves none of the real hard problems. It's just a nice data warehouse. The entire thing is federated queries. That is the key in the life science domain. If you don't support federated queries, you can just as well go home because there was no point to it. Spin is just RDF serialization of Sparkle queries. And if you can execute them, you can ship them. And there's some really, really nice things you can do with them. And I hope that you get better standardization in the data shapes work group. But I think, other than that, I think it's fantastic technology and I really like it. There's not much I can say about that.